Hello viewers, welcome to online course on Mathematics 3. This course basically for undergraduate student or BTech student of engineering field. Today we are going to discuss about the Bessel's equation and Bessel's function of partial differential equation and the series solution of ordinary differential equation. Myself Sanjay Vishwas, Assistant Professor of Mathematics, Department of Applied Science and Humanities of Guru Nanak Institute of Technology. So here is my details of contact information. If you have facing any kind of problem regarding my online class, you can call me or send message through my mail ID. Before we start today's lecture, let's quickly recall in the last lecture. So in the last lecture we have discussed about the series solution of ordinary differential equations. Okay, in the chapter of partial differential equation and series solution of ordinary differential equation. So in this chapter we have discussed about the introduction of series solution of ODE, that is the Taylor series about the point x is equal to x0, and after that we have talked about the validity of the series solution, and then we have talked about the general method to solve the ordinary differential equation and the Frobenius method to solve the ordinary differential equations. Okay. So the general method is used when the points is a ordinary point, and Frobenius method is used when the point of a ordinary differential equation is a regular singular point. Okay. So today we are going to discuss about the Bessel's equation and Bessel's function, and this is my fifth lecture on partial differential equation and the series solution of ordinary differential equation. Here is the content of today's lecture. So in this lecture, first of all, we will discuss about the definition of Bessel's equation, and after that we will talk about the solutions of Bessel's differential equation, and then we will discuss about the series solutions of Bessel's equations as well. And then we will study on the recurrence relation and Bessel's functions. Okay, and some related examples we will discuss in lecture 5 of module 4, that means the Bessel's equation and the Bessel's function. At first we will begin with the definition of the Bessel's equation. So here is the definition: the differential equation of the form x square into dy dx2 plus x into dy dx plus x square minus n square into y is equal to 0. Okay, this is the second order differential equation, ordinary differential equation. Or this equation can be written as, after divided by x square on both sides, we will get d2y dx2 plus 1 by x dy dx plus 1 minus n square by x square into y is equal to 0, and we can write it equation number 1. So this equation is called the Bessel's equation of order n, where n being a non-negative constant. Okay, so the Bessel's equation of a differential equation is of the form is either this one, that means x square d2y dx2 plus x dy dx plus x square minus n square of y is equal to 0, where n be any non-negative constant, or it can be written as d2y dx2 plus 1 by x dy dx plus 1 minus n square by x square of y is equal to 0. Okay, so here is the solution of the Bessel's equation. So now we solve equation 1, that means the Bessel's equation in series by using the well-known method of Frobenius. Okay, so I have already discussed the Frobenius method in the previous chapter. Okay, so how to solve the ordinary differential equation by Frobenius method. Okay, so let the series solution of equation 1 be y is equal to summation over m is equal to 0 to infinity m into x minus a whole to the power m plus k, where a0 is not equals to 0. Okay, so this is the series solution of the given differential equation, that means the Bessel's equation. Okay, and therefore the first order differentiation of the required solution, that means y is equal to summation m is equal to 0 to infinity m into x minus a whole to the power m plus k, and the first differentiation, it will be dy dx is equal to summation over m is equal to 0 to infinity m into m plus k into x minus a whole to the power m plus k minus 1. Okay, this is the first order differentiation of this series, that means equation 2. And d2y dx, to the second order differentiation, it will be summation over m is equal to 0 to infinity m into m plus k into m plus k minus 1 into x minus a whole to the power m plus k minus 2. This is the second order differentiation. Okay, so now substituting these values in equation 1, that means in a Bessel's equation, we get x square into summation over m is equal to 0 to infinity m into, so this one is the second order differentiation of the series solution, that means m into m plus k into m plus k minus 1 into x to the power m plus k minus 2. Okay, this is the second order differentiation, plus x into summation over m is equal to 0 to infinity m into m plus k into x to the power m plus k minus 1. This is the first order differentiation of the required series solution. Okay, plus x square minus n square into y, and where y is equal to summation over m is equal to 0 to infinity m into x to the power m plus k, and this is equals to 0. And after multiplying by x square on the first term and x on the second term, and from this we will get summation over m is equal to 0 to infinity m into m plus k into m plus k minus 1. Okay, plus x to the power m plus k, after multiply by x square on that summation, we will get this one, plus m plus k into x to the power m plus k, after multiply by x, we will get x to the power m plus k. Okay, minus n square. So after multiplying by x square on the first summation, x by second summation, and n square by the third term, that means the third summation, will get a summation over m is equal to 0 to infinity m into m plus k into m plus k minus 1 plus m plus k minus n square of x to the power m plus k. And in that case, where x to the power m plus k take as a common, plus summation over m is equal to 0 to infinity m into x to the power m plus k plus 2 is equal to 0. Okay, so the above equation, that means the series solution, is reduced to this equation, and after that we will get from the above equation summation over m is equal to 0 to infinity m into m plus n plus k. Okay, after simplifying this equation, we will get this one, m plus n plus k into m plus k minus n of x to the power m plus k plus summation over m is equal to 0 to infinity m into x to the power m plus k plus 2 is equal to 0, and we can write it equation number 3. So after putting the value of y double dash, y dash, and y, and then from the Bessel's equation we will get this equation, that means the equation 3. Okay, after simplifying this, we will get this one. So now equating to 0 the smallest power of x, namely x to the power k. Okay, so when m is equal to 0, we will get x to the power k in equation 3. So and which gives the identical equation is a0 into, okay, when we put m is equal to 0, then that means the first term of the equation 3 will reduce to a0 into k plus n into k minus n is equal to 0. Okay, so from this we will get k is equal to plus n and minus n, that means plus minus n, where a0 is not equals to 0. So the root of the identical are n and minus n. So next, equating to 0 the coefficient of x to the power k plus 1. Okay, so x to the power k is the smallest power of x when m is equal to 0, and x to the power k plus 1 is the next smallest power of x when we put m is equal to 1, and from the first term of the equation 3, it will give a1 into k plus 1 plus n. Okay, when we put m is equal to 1 in that section, we will get this one, a1 into k plus 1 plus n into k plus 1 minus n is equal to 0. So from this equation we will get a1 is equal to 0, for k is equal to n comma minus n. Okay, and here you know k is equal to n and minus n, so from after putting this value we get a1 is equal to 0. And lastly, equating to 0 the coefficient of x to the power k plus 1, and this will give m into k plus m plus n into k plus m minus n plus a m minus 2 is equal to 0. Okay, and you know this is the recurrence relation of the given differential equation. So from this we'll get m is equal to minus a m minus 2 by k plus m plus n into k plus m minus n. Okay, so after simplifying this equation we'll get this one, m is equal to this, and we can write it equation number 4. And this relation is called a recurrence relation of the given differential equations. Okay, so now we put m is equal to 3, 5, 7, 9 and up to infinity in equation 4, and using a1 is equal to 0, and from this we will get a3 is equal to 0, where a1 is equal to 0, you know, a5 is equal to 0, a7 is equal to 0, okay, and a9 is equal to 0, and so on. So therefore a1 is equal to a3 is equal to a5 is equal to a9 is equal to a11, okay, are all 0. And now two cases arise. So case number 1, when k is equal to n. Okay, so from equation 4 we have, by putting successively m is equal to 2, 4, 6, 8, that means the even number, we get a2 is equal to minus 1 by k plus 2 plus n, okay, into k plus 2 minus n of a0. a4 is equal to minus 1 by k plus 4 plus n into k plus 4 minus n into a2. So after putting the value of a2 in this equation, we will get minus 1 by k plus 4 plus n, k plus 4 minus n, k plus 2 plus n into k plus 2 minus n of a0, and so on. Okay, so from this relation, that means equation 4, this is the recurrence relation of the given differential equation, and if we put the odd numbers where m is equal to 3, 5, 7 up to infinity, we'll get a1, a3, a5 are all 0. But when we put m is equal to 2, 4, 6, that means the even number, okay, so we'll get to this one. So a2 is equal to this, a4 is equal to this, okay, and so on. So therefore, by putting these values in equation 2, we get y is equal to a0 into x to the power k, where a1, a3, a5, a7 are all 0, okay. So y is equal to a0 into x to the power k into 1 minus x square by k plus 2 plus n into k plus 2 minus n, okay, this is the second term, plus x to the power 4 by k plus 4 plus n into k plus 4 minus n into k plus 2 plus n into k plus 2 minus n, and up to infinity. Okay, and for k is equal to n, we have y is equal to a0 into x to the power n. When we put k is equal to n, in that series solution, we get y is equal to a0 into x to the power n into 1 minus x square by 4 into 1 plus n. Okay, when we put k is equal to n, in that equation we will get this one, plus x to the power 4 by 4 into 8 into 1 plus n into 2 plus n, okay, and up to infinity. So if we take a0 is equal to 1 by 2 to the power n into gamma n plus 1, this is the gamma function, okay, and can be written as gamma of n plus 1, and this solution is called the Bessel's function of the first kind of order n, and is denoted by Jn of x, where gamma of n is the gamma function, okay, is the gamma function. So therefore Jn of x, and this is the Bessel's function of the given series. Therefore the solution of the given Bessel's equation, it is equals to the Bessel's function, and it is denoted by Jn of x, and Jn of x is equal to x to the power n by 2 to the power n into gamma n plus 1 into 1 plus minus 1 into x square by 2 square into 1 factorial into n plus 1 This is the second term, plus minus 1 whole to the power 2, that means plus 1 into x to the power 4 by 2 to the power 3 into, this is actually 2 to the power 3 is equal to 8 into 2 factorial n plus 1 into n plus 2 and up to infinity. And this series solution can be written as x to the power n by 2 to the power n into gamma n plus 1 into summation of r is equal to 0 to infinity, okay, minus 1 whole to the power r into x to the power 2r by 2 to the power r factorial into n plus 1 into n plus 2 into and up to n plus r. And this is equals to, you know, n plus 1 into n plus 2 into n plus 3 into n plus 4, okay, and up to n plus r, and it is actually the gamma function, okay, and it is equals to gamma of n plus r plus 1. So therefore the Bessel's function of order n, and it is denoted by Jn of x, and it can be defined as Jn of x is equal to summation of r is equal to 0 to infinity minus 1 whole to the power r into x by 2 whole to the power n plus 2r into 1 by r factorial into gamma of n plus r plus 1, okay. So this is called the Bessel's function of order n. So after that, when we put k is equal to minus n, then the series solution is obtained by replacing n by minus n and in the value of j, and it can be written as j of minus n of x, okay. And this is also the Bessel's function, and it is equals to summation of r is equal to 0 to infinity minus 1 whole to the power r into x by 2 whole to the power minus n plus 2r. So in that case, when we put n is equal to minus n, okay, and then the Bessel's function of order n, and it is reduced to j of minus n of x is equal to this summation of r is equal to 0 to infinity minus 1 whole to the power r into x by 2 whole to the power minus n plus 2r into 1 by r factorial into gamma of minus n plus r plus 1. So when n is not integer, then j of minus n of x is distinct from jn of x, okay, otherwise these two values are same. So the solution of the Bessel's equation are called the Bessel's functions, and the general solutions of the Bessel's equations is y is equal to a into j of minus n of x plus b into jn of x, okay, where j of minus n of x and jn of x are given, and these are the Bessel's function of the solution of the Bessel's equation, okay, where a and b are the arbitrary constant, and these two Bessel's functions are distinct when n is not an integer. Let us move on the next slide. So in this slide we will discuss about the series solution of the Bessel's equation, okay. So here is the differential equation d2y and dx2 plus 1 by x dy dx plus y is equal to 0, and we can write it equation number 1. And this differential equation is known as the Bessel's equation for n is equal to 0. So in that case, where n is equal to 0. Now we are going to solve the Bessel's equation by the method of Frobenius. So let the series solution of the equation 1, that means the Bessel's equation, and it will be y is equal to summation of our m is equal to 0 to infinity m into x to the power m plus k, where a0 is not equals to 0, and we can write it equation number 2. So this is the general solution of the Bessel's equation 1, okay. So now we differentiate this equation with respect to x, we will get dy dx is equal to summation of our m is equal to 0 to infinity m into the derivative of x to the power m plus k, it will be m plus k into x to the power m plus k minus 1. Again we differentiate this, we will get d2y dx2, and it is equals to summation of our m is equal to 0 to infinity m into m plus k and derivative of x to the power m plus k minus 1, and it will be m plus k minus 1 into x to the power m plus k minus 2, okay. So this one is the second order differentiation, and this is the first order differentiation for the function y, okay. So now substituting these values in equation 1, that means in the Bessel's equation, and we get summation of our m is equal to 0 to infinity m into m plus k whole square x to the power m plus k minus 2 plus summation over m is equal to 0 to infinity m into x to the power m plus k, and we can write it equation number 3. So after simplifying this equation, we'll get this one. Okay, so which is an identity. So now equating to 0 the coefficient of the lowest power of x. Okay, so the when we put m is equal to 0, so we'll get x to the power k minus 2. So the lowest power of x to the power k minus 2, and it will be uh, a0 into k square. Okay, and it is 0. That means a0 into k square is equal to 0. So from this we'll get k is equal to 0 comma 0, where a0 is not equals to 0. Okay, so now the equating to 0 to the coefficient of the next power of x, that means when we put m is equal to 1, we will get x to the power k minus 1. Okay, so the coefficient of x to the power k minus 1, and it will be, a1 into k plus 1 whole square is equal to 0. So from this we'll get a1 is equal to 0 for k is equal to 0. Okay, again equating to 0 the coefficient of the general term, that means x to the power k plus m, and from the above equation we have a m plus 2 into k plus m plus 2 whole square plus m is equal to 0. And after simplifying this equation, we will get the value of am plus 2, and it will be minus am by k plus m plus 2 whole square. Okay, and we can write it equation number 4. And this relation or equation is called the recurrence relation of the given Bessel's equation or the ordinary differential equation. So now we put m is equal to 3, 5. Now we put m is equal to 1. Then from the above relation we will get a3 is equal to 0. So you know that a1 is equal to 0. Okay. And similarly, when we put m is equal to 3, then we will get a5, and a5 is equal to, again it is 0. a7 is 0, a9 is 0. So when m is an odd integer, that means odd positive integer, then a1, a3, a5, a7 are all 0. And next we will put m is equal to 0, 2, 4, 6. Okay, that means m be an even number, that means 2, 4, 6, 8, 10, and up to infinity. In equation 4 successively we get a2 is equal to minus a0 by k plus 2 whole square, a4 is equal to minus a2 by k plus 4 whole square. Okay, that means when we put a2 is equal to this, we'll get minus a0 by k plus 2 whole square into k plus 4 whole square, and so on. So hence from equation 2, that is the required general solution of the given Bessel's equation, and it is equals to y is equal to a0 into x to the power k into 1 minus x square by k plus 2 whole square. Okay, after putting the value of a0, a1, a2, a3, a4, where a1, a3, a5, a7 are all 0, and a2 is equal to this, a4 is equal to this. Okay. So from this we will get a0 into x to the power k into 1 minus x square by k plus 2 whole square plus x to the power 4 by k plus 2 whole square into k plus 4 whole square, and up to infinity. Okay. So this is the general solution of the given Bessel's equation. So from this equation, when we put a k is equal to 0, and we'll get y is equal to a0 into 1 minus x square by 2 square plus x to the power 4 by 2 square into 4 square minus x to the power 6 by 2 square into 4 square into 6 square. Okay, and up to infinity. And if a0 is equal to 1, then the above equation is denoted by j0 of x, where j0 of x is the Bessel's function of 0th order. Okay, and it is equals to 1 minus x square by 2 square plus x to the power 4 by 2 square into 4 square minus x to the power 6 by 2 square into 4 square into 6 square, and up to infinity. Okay, so where j0 of x is called the Bessel's function of the 0th order. Okay, and it can be written as 1 minus x square by 2 square plus x square x to the power 4 by 2 square into 4 square minus x to the power 6 by 2 square into 4 square into 6 square and up to infinity. So after that we will take some recurrence formula for the Bessel's function. So the first recurrence formula, it will be ddx of x to the power n into jn of x. So jn of x, the nth order Bessel's function. Okay, so it is equals to x to the power n jn minus 1 or x into jn dash x, is the first order differentiation of jn x, is equal to minus x into jn x plus x into jn minus 1 of x, where jn x is the nth order Bessel's function and jn minus 1 of x is the n minus 1th order Bessel's function. Okay, this is the recurrence relation or the recurrence formula for the Bessel's equation or the Bessel's function. Okay. So here is the proof of the first recurrence formula, and we know that the nth order Bessel's function jn of x is equal to summation over r is equal to 0 to infinity. This is the formula of the nth order Bessel's function. Jn of x is equal to summation over r is equal to 0 to infinity minus 1 whole to the power r into x by 2 whole to the power n plus 2r into 1 by gamma r plus 1 or r factorial into gamma n plus r plus 1. Okay, this is the nth order Bessel's function. So now we multiply by x to the power n on the nth order Bessel's function. We'll get x to the power n into jn of x, and it will be summation over r is equal to 0 to infinity minus 1 whole to the power r. Okay, after multiplying by x to the power n, it will be changed. So it will be x to the power 2 into n plus r into 1 by 2 to the power n plus 2r. Okay, where x by 2 is equal to, whole to the power n plus 2r is equal to x to the power n plus 2r by 2 to the power n plus 2r. Okay, and after multiplying by x to the power n, we will get x to the power 2 into n plus r by 2 to the power n plus 2r. Okay, into 1 by gamma r plus 1 into gamma n plus r plus 1. So now differentiate this equation with respect to x, and we'll get ddx of x to the power n of jn x. Okay, and it is equals to summation over r is equal to 0 to infinity minus 1 whole to the power r into, so the derivative of x to the power 2 n plus r is equal to 2 into n plus r into x to the power 2 into n plus r minus 1. Okay, so this is the first order differentiation with respect to x into this one. This is the constant term. Okay, so 1 by 2 to the power n plus 2r into gamma n plus 1 into gamma n plus r plus 1. And this summation will reduce to x to the power n, okay, into summation over r is equal to 0 to infinity minus 1 whole to the power r into x by 2 whole to the power n minus 1 plus 2r. Okay, after taking x to the power n as common from this summation, we will get this one, minus 1 whole to the power r into x by 2 whole to the power n minus 1 plus 2r into 1 by gamma r plus 1 into gamma n minus 1 plus r plus 1. So after cancelling the term 2 into n plus r, we will get this one. Okay, and this is the n minus 1th order Bessel's function. Okay, so ddx of x to the power into jn of x, that means the nth order Bessel's function, and it will be x to the power n into jn minus 1 of x. So hence the proof of the first part of the recurrence formula, and the second part, it will be after differentiation, we will get x to the power n into jn dash of x. Okay, the derivative of jn x is equal to jn dash x plus derivative of x to the power n. So it will be n into x to the power n minus 1 into jn of x. In that case, where jn of x is constant. Okay, so this is equals to x to the power n into jn minus 1 of x. So after derivative, we'll get this equation, okay, from the above equation. And after cancelling the term x to the power n minus 1 on both sides, we'll get x into jn dash x is equal to minus n into jn of x plus x into jn minus 1 of x. Hence the proof of the second part of the recurrence formula. So after that we'll take one more recurrence formula. So this is the second one. So the first derivative, that is ddx of x to the power minus n of jn of x is equal to minus of x to the power minus n of jn plus 1 of x. Okay, so where jn plus 1 of x is the n plus 1th order Bessel's function, or x into jn dash of x, jn dash is the first order differentiation of jn x, is equal to n into jn x minus x into jn plus 1 of x. Okay, so you know the nth order Bessel's function, and it will be summation of r is equal to 0 to infinity minus 1 whole to the power r into x by 2 whole to the power n plus 2r into 1 by gamma r plus 1 into gamma n plus r plus 1. Okay, so this is the formula of the nth order Bessel's function, you know. So now multiple by x to the power minus n on both sides, we'll get x to the power minus n into jn of x, and this is equals to summation of r is equal to 0 to infinity minus 1 whole to the power r. Okay, and you know x by 2 whole to the power n plus 2r is equal to x to the power n plus 2r by 2 to the power n plus 2r, and after multiple by x to the power minus n on that summation, will get x to the power 2r, okay, into 1 by 2 to the power n plus 2r gamma r plus 1 into gamma n plus r plus 1. So this term is fixed in that case. So now differentiate this equation, we'll get ddx of x to the power minus n of jn x, and this is equals to summation of r is equal to 0 to infinity minus 1 whole to the power r into derivative of x to the power 2r, and it will be, you know, 2r into x to the power 2r minus 1 into this term. This is actually the constant, so derivative of this is constant, so that is 1 by 2 to the power n plus 2r into gamma of r plus 1 into gamma of n plus r plus 1. Now taking minus of x to the power minus n as common, then the above equation is reduced to ddx of x to the power minus n of jn x is equal to minus of x to the power minus n into summation of r is equal to 1 to infinity. In that case, where the summation r is starting from 1 to infinity. Okay, so into minus 1 whole to the power r minus 1, x by 2 whole to the power n plus 1 plus 2 into r minus 1. So after simplifying this equation, we'll get this one into 1 by gamma of r minus 1 plus 1 into gamma of n plus 1 plus r minus 1 plus 1. Okay, so this function is reduced to this one, that is the gamma function. This can be written as this, and you know the gamma of r is equal to infinity when r is equal to 0. So the term corresponding to r is equal to 0 vanish. So that means, you know, 1 by infinity is equal to 0 when we put r is equal to 0. Therefore, the above equation is reduced to minus x to the power minus n into summation of r m is equal to 0 to infinity. So in that case, r minus 1 is equal to m. So minus 1 whole to the power n into x by 2 whole to the power n plus 1 plus 2 into m into 1 by gamma m plus 1 into gamma n plus 1 plus m plus 1. So by putting m is equal to r minus 1, and you know this is actually the Bessel's function of order n plus 1. So ddx of x to the power minus n of jn x is equals to minus of x to the power minus n of jn plus 1 of x. Hence the proof of the first part of the recurrence relation. So now we differentiate this equation, that means ddx of x to the power minus n of jn x. So after differentiation this equation, we'll get x to the power minus n of jn dash x minus derivative of x to the power minus n is minus of n into x to the power minus n minus 1 of j n x. Okay, and it is equals to minus x to the power minus n of j n plus 1 of x. And after cancelling the term x to the power minus n minus 1 on both sides, we will get x into j n dash x is equal to n into j n of x minus x into j n plus 1 of x. So here's the proof of the second part of the second recurrence relation. Okay, so after that we will take one more recurrence formula, and that means 2 into j n dash x is equal to minus n into j n minus 1 of x minus j n plus 1 of x. Okay, so here is the proof of the third recurrence formula. So from the recurrence formula 1 and 2, we have, in the first recurrence formula we have seen that x into j n dash x is equal to minus x into j n x plus x into j n minus 1 of x. Okay, this is the first recurrence formula we have already discussed in this lecture. And the second one, it will be x into j n dash x is equal to n into j n x minus x into j n plus 1 of x. And we can write it equation number 2. So adding equation 1 and 2, we will get 2x into jn dash x is equal to x into jn minus 1 of x minus x into jn plus 1 of x. Okay, so after cancelling the term x on both sides, we will get 2 into jn dash x is equal to n minus 1 of x minus n plus 1 of x. Hence the proof of the third recurrence formula. Let us move on the next slide. So in this slide we will discuss some related examples on Bessel's function. So that when n is a positive integer, and then g of minus n of x is equal to minus 1 whole to the power n of j n x, and the second one, j n of minus x is equal to minus 1 whole to the power n g n of x for positive or negative integers. Okay, so in both cases the result is same, that means g of minus n of x is equal to this, as well as g n of minus x is equal to minus 1 whole to the power n of g n x. Okay, so here is the solution of the given problem. So g of minus n of x, from the definition of the Bessel's function, it is equals to summation of r is equal to 0 to infinity minus 1 whole to the power r x by 2 whole to the power minus n plus 2r into 1 by r factorial or gamma r plus 1 into gamma of minus n plus r plus 1. Okay, so this is the definition of the Bessel's function. So now since if p is an integer, and then gamma of minus p is infinity for p greater than 0. Okay, so we get terms in g of minus n equal to 0 till minus n plus r plus 1 is less than 1, that means r is less than n. So hence we can write g of minus n of x is equal to summation of r is equal to 0 to infinity minus 1 whole to the power r x by 2 whole to the power minus n plus 2r into 1 by r factorial into gamma minus n plus r plus 1. Okay, so now we put r is equal to n plus n, then the above Bessel's function is reduced to summation of r s is equal to 0 to infinity, okay, minus 1 whole to the power n plus s into x by 2 whole to the power n plus 2s into 1 by n plus s factorial into gamma s plus 1. Okay, and this equation is reduced to minus 1 whole to the power n into summation of r s is equal to 0 to infinity minus 1 whole to the power s into x by 2 whole to the power n plus 2s into 1 by s factorial into gamma of n plus s plus 1. So minus 1 whole to the power n is a constant, and this summation is called the Bessel's function of order n. Okay, so from this we will get minus 1 whole to the power n into gn of x. So this is the proof of the first part of the given problem, and after that we will discuss about the second part of the given problem. So we know that the nth order Bessel's function, it will be summation over r is equal to 0 to infinity minus 1 whole to the power r into x by 2 whole to the power n plus 2r into 1 by r factorial into gamma of n plus r plus 1, and we can write it equation number 1. So there are two cases. The first case, it will be when n is positive integer, and the second case when n be a negative integer. Okay, so when n be a positive integer, then replacing x by minus x in equation 1, we get g of minus x is equals to summation over r is equal to 0 to infinity minus 1 whole to the power r, okay, into minus x by 2 whole to the power n plus 2r into 1 by r factorial into gamma n plus r plus 1. After simplifying this equation, we'll get minus 1 whole to the power n summation over r is equal to 0 to infinity minus 1 whole to the power r, okay, into x by 2 whole to the power n plus 2r. So you know, in that case where minus 1 whole to the power 2r is equal to 1, but minus 1 whole to the power n, it is either positive or negative. Okay, that means minus 1 whole to the power n into 1 by r factorial into gamma n plus r plus 1, and you know this is actually the Bessel's function of order n. So Jn of minus x, that is nth order Bessel's function of the function minus x, it is equals to minus 1 whole to the power n into Jn of x. So in that case, when n be a positive integer, as well when n be a negative integer, so let n is equal to minus n. Okay, so where n be a positive integer, that means n is negative. Therefore, from the Bessel's function or the recurrence relation, we have seen that Jn of x is equal to j minus n of x. Okay, and this is equals to, you know, minus 1 whole to the power n into Jn of x, and we have already discussed in the previous slide. So now replacing x by minus x in equation 1, we have Jn of minus x, it is equals to minus 1 whole to the power m, okay, into Jm of minus x, and it is equals to where Jm of minus x is equal to, you know, minus 1 whole to the power m into Jm of x by case 1. Okay, so minus 1 whole to the power m into, and minus 1 whole to the power m Jm of x is equal to j minus m of x, you know that. Okay, so this is equals to this minus 1 whole to the power m into j minus m of x, and therefore the above equation can be written as Jn of minus x is equal to minus 1 whole to the power 2m into minus 1 whole to the power minus m, and is equals to, you know, minus 1 whole to the power n. So minus 1 whole to the power n can be written as a product of minus 1 whole to the power 2m into minus 1 whole to the power minus m into j of minus m of x. Okay, and you know, when minus 1 whole to the power 2m is equal to 1, so 2m is a positive integer, where 2m is a even number, so minus 1 whole to the power even number is a plus 1. So minus 1 whole to the power minus m of j of minus m of x, and you know, I have taken it minus m is equal to n, so after replacing minus m is equal to n, we get minus 1 whole to the power n into jn of x. Okay, so in both cases jn of minus x is equal to minus 1 whole to the power n of jn of x. That means for positive and negative integer of n. Okay, so hence the proof of the second part of the given problem. So after that, we'll take one more examples on the Bessel's function. This is also the properties of the Bessel's function. So that j of minus half of x is equal to root over of 2 by pi x into cos x, and j of 1 by 2 of x is equal to root over of 2 by pi x into sin x. So here is the proof of the given properties of the Bessel's function. So we know that the nth order Bessel's function, and it can be written as x to the power n by 2 to the power into gamma n plus 1 into 1 minus x square by 2 into 2n plus 2 plus, this is the another form of the nth order gamma function. This is the another form of the nth order Bessel's function. Okay, so 1 minus x square by 2 into 2n plus 2 plus x to the power 4 by 2 into 4 into 2n plus 2 into 2n plus 4, okay, and up to infinity. So now we put x is equal to minus 1 by n in the above equation. That means in equation 1 we get g of minus half of x. Okay, this is the Bessel's function, okay, of order minus half. So it is equals to, after putting the value of x is equal to minus half, we will get x to the power minus half by 2 to the power minus half into gamma half into 1 minus x square by 2 into 1 plus x to the power 4 by 2 into 4 into 3 into 1, okay, and up to infinity. And after simplifying this equation, we'll get j of minus half of x, and it is equals to, so x to the power minus half is equal to 1 by root x, 2 to the power minus half is equal to 1 by root over of 2, and gamma half is equal to, you know, root over of pi. So after simplifying this, we'll get root over of 2 by pi x into 1 minus x square by 2 factorial. So 2 into 1 is equal to 2 factorial, you know. 4 into 3 into 2 into 1 is equal to 4 factorial. So 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial. Okay, so up to infinity. And this is the series of cos x. You note it. So therefore g of minus half of x, and it is equals to root over of 2 by pi x into cos x. So hence the proof of the first properties of Bessel's function. And after that we will put x is equal to half in equation 1. We get j half of x is equal to x to the power half 2 to the power half into gamma 3 by 2. Okay, so gamma 3 by 2 is equal to 1 by 2 into gamma half, that means 1 by 2 into root pi into 1 minus x square by 2 into 3 plus x to the power 4 by 2 into 4 into 3 into 5. Okay, so up to infinity. So therefore after simplifying this equation, we'll get root over of x by 2 into 1 by half into root pi into 1 by x, okay, into 1 minus x to the power 3 by 3 factorial plus x to the power 5 by 5 factorial, and up to infinity. And this is the series function of the sin x, you know that. So this is equals to root over of 2 by pi x into sin x. So hence the proof of the second properties of the Bessel's functions. So that means g of minus half of x is equal to root over of 2 by pi x into sin x. And after that we'll take an example on the Bessel's function. So here is the example. Express j4 in terms of j0 and j1. Okay, so from the recurrence relation, you know that jn plus 1 of x, this is the recurrence relation of the Bessel's function. It is equals to 2n by x into jn of x minus jn minus 1 of x, and we can write it equation number 1. We get by putting n is equal to 3 and 2, and from the equation 1 we get j4 of x is equal to 6 by x into j3 of x minus j2 of x after putting the value of n is equal to 3, and n is equal to 2 will get j3 of x is equal to 4 by x into j2x minus j1x. Okay, so after putting the value of j3 of x in the above equation, that means in the first equation we'll get j4 of x is equal to this. Okay, that means 6 by x into 4 by x into j2x minus j1x minus j2 of x. So again from equation 1 we'll get j2 of x is equal to, when we put n is equal to 1, we'll get this one, 2 by x into j1 of x minus j0 of x. And putting the value of j2 of x in the above equation, that means in that equation we'll get j4 of x is equal to 48 by n to the power 3. So after simplifying this equation, we'll get this one. So 48 by n to the power 3 minus 8 by n into j1 of x minus 24 by n square minus 1 into j0 of x. So the Bessel's function j4 of x can be expressed in terms of j1 and j0. That means j4 of x is equal to 48 by n to the power 3 minus 8 by n into j1x minus 24 by n square minus 1 into j0 of x. I will stop here. Thank you.